It was not until about, well, the 1800s when the value of fossils as geologic tools became truly apparent. William Smith, which was a British engineer and a canal builder, discovered that each rock formation in the canals where he worked contained fossils unlike those in the beds either above or below. Further, he also noted that some of the sedimentary strata that were widely separated in terms of geographic location could also be identified using the principle of superposition and the principle of lateral continuity. And so with the help of the fossils within the strata, he was able to do this. He came up with the principle of fossil succession. The principle of fossil succession states that fossil organisms success one another in a definite and determinable order, and therefore any time period can be recognized by its fossil content. So that all sounded kind of hard. So in other words, fossils are arranged according to their age. So documenting the evolution of life through time is how they present. Smith later built the fossil record of Britain as he was working within this canal system, which later on helped him to make the first geologic map of Great Britain and also was the first geologic map ever to be made in the world. So once fossils were found to be time indicators, they became the most useful means of correlating rocks of similar ages in different regions or across different regions. One second. Index fossils are primarily important and useful for doing this correlation of ages across different regions. Index fossils are fossils that have to meet two conditions. They are fossils of organisms that were widespread, so they lived in a lot of areas, and they are fossils they're from organisms that lived a short period of time, so a fairly short lifespan. It also helps if they are easily identifiable, meaning different from others that are nearby. So the picture on the slide shows many of the index fossils and the time during which they were present, which is represented by the rocks that they were found in. These index fossils aren't always present in the different rock formations, or perhaps some formations have more than one index fossil, for example. So in those cases, a fossil assemblage is very useful to establish the age of that specific bed. So the figure here on the slide shows how this fossil assemblage can be done based on the span during which these organisms lived. So if you know the span during which they were present in the world, and you can find an assortment or an assemblage of these fossils, these index fossils, then you will be able to find out the time during which they all lived at the same time, and hence narrow down the possibilities for a specific age. So, if, for example, you're trying to determine the age of unit A or B within that slide, the type of index fossils that they contain make it have to be a specific age. So we'll practice this during lab, but you see that basically the presence of this fossil right here, this fossil right here, and this fossil right here being short-lived and widespread make it easy enough for units A and units B to be identified specifically. And also, aside from being amazing tools for correlation, fossils, and for dating tools themselves, their presence in a specific rock suggests certain types of environments of formation of deposition. So, for example, the presence of a bivalve, which is kind of like a clam or an oyster, suggests a fairly shallow marine or potentially kind of lake environment. Or as was the case, for example, when Alfred Wegener did his fossil correlation in order to come up with the continental drift hypothesis, the presence of Glossopteris, which is that fern-like plant, which is typical of mid-latitudes, suggested that the places where it was found, which are currently tropical latitudes, were once closer to the South Pole. So they represent different environments during which they formed at, or during which they got fossilized at. Okay, so in addition to establishing relative dating techniques, so again, those principles and those unconformities that we looked at, as well as fossils as dating tools, using fossils to correlate across different regions and also find out different ages of the rock units, scientists can also obtain reliable numerical dates for events within the geologic past. For example, we know that the Earth is 4.6 billion years old, and another example is that dinosaurs became extinct about 65 million years ago. So we are able to get these numbers through radiometric dating. And radiometric dating allows us to date the vast amount of time that is recorded within a set of rocks in a quantitative way, rather than in a simple qualitative manner of the rock's characteristics. Okay, so before we get into the specifics of radiometric dating, we must cover a little bit of radioactivity. So, if you remember from chapter 3, you may recall that atoms have three main parts. They have protons, which are charged positively. They have neutrons, which have no charge. Both the protons and the neutrons make up the nucleus of an atom, and they are typically the same number within that atom. And also the atom is going to contain a third part, which is called an electron. The electrons have a negative charge and are typically orbiting the nucleus in a fairly disorganized way. So the atomic number is each element's identifying number, and it is equal to the number of protons in the nucleus. Every element has a different number of protons, which makes each element have a specific identifying number. And all of the atoms of that element will have the same number of protons. So if the atomic number will stay constant, that means that the number of protons is the same. So practically all of the mass in an atom is in the nucleus. Electrons' mass is almost negligible. So the atomic mass is basically the addition of protons and neutrons together. The number of neutrons in an atom can vary, however, unlike the number of protons. So the variations in the number of neutrons within an atom gives it a different atomic mass. So these variations is what we call isotopes. So I'm going to refer to these a lot. So if you need to pause the video and listen to what I just said about neutrons, go ahead and do so. An example of this is shown in the image right here below. So, for example, carbon has 6 protons, so its atomic number is 6. It typically also has 6 neutrons, making the mass of carbon 12. However, sometimes it's going to have 7 neutrons, in which case the mass is 13. And in certain cases, it may also have 8 neutrons, which makes the mass 14. These 3 variations are different isotopes of carbon. And the last one that I mentioned, so the one that has 8 neutrons, is a radioactive isotope of carbon, which I'll talk about in the next few slides. Okay, so not all of the isotopes are radioactive. Some of them are stable, but they are not necessary or they're a little bit of the specific scope of this part of the lecture. So I'm not going to talk about it much. Okay, so typically in an atom, the forces that stabilize the nucleus tend to be very strong. However, when you have radioactive isotopes, those forces that bind the protons and the neutrons together are not strong enough to keep them together forever, which makes those nuclei, I should say, more unstable. And being unstable, it will spontaneously break apart in a process that is called nuclear decay or radioactive decay. So, as time goes by, more and more of the unstable atoms decay, producing a growing number of stable isotopes. The unstable isotopes that decay we call parent material or parent isotopes, and the decayed stable ones we call daughter material or daughter isotopes. So there are three ways, or there are three more common ways in which nuclear decay can occur, and those can be seen in the picture on the slide, but we'll go through them real fast. So the first one is alpha emission. So here, alpha particles may be emitted from the nucleus itself. So an alpha particle is constituted by two protons and two neutrons, which means that an alpha emission results in the atomic number being reduced by 4, and that the atomic mass is going to be reduced by 4, and that the atomic number is reduced by 2, because you lose 2 protons and 2 neutrons. The second type of decay is going to be beta emission. Here, a beta particle, which is also just an electron, is emitted from the nucleus when a neutron decays to produce 1 electron and 1 proton. So neutrons are kind of weird. I did say that they had no charge, but sometimes a neutron itself can decay in producing 2 particles, an electron and a proton, one charged either way. So when it does this, the electron that is produced exits or is emitted from the nucleus itself as the neutron decays, and you have the electron being emitted. So because electrons have almost no mass, the atomic mass of that atom remains the same as the electron exits. However, the atomic number increases by 1, because now you have an added proton to that nucleus. The third type of decay is called electron capture. So here, as the name says, an electron is captured by the nucleus. This electron will then combine with one of the existing protons in order to make a neutron. So neutrons can be decayed, or they can be made by the addition of a proton or an electron itself. So in this case of electron capture, there is no mass that is added, since electrons have such little mass that is negligible. But overall, the atomic number is lowered by 1, because a previous proton is now a neutron, which, again, the proton combining with the electron caused it to be 1 atomic number lower. So the decay of radioactive parent isotopes overall is however, not always as straightforward as I put it just now. For example, the isotopic atom uranium-238 is one of the most useful isotopes for radiometric dating. And this specific isotope has to undergo 8 different alpha emissions and 6 beta emissions before finally becoming the stable daughter isotope, which is lead-206. So, and I'll show you the graph of that transition in a little bit. So you see the complexity of how many decays it has to undergo until it becomes stable.